All right, sixth grade. Today we're going to talk about landforms that are caused by deposition. So last week we talked about landforms that were caused by uh, erosion, so the moving away of material. Deposition is the opposite of that, which means that it's going to be, think of like depositing into a bank. That's where that root word comes from. It's when something gets left behind or deposited somewhere. We're going to get these types of landforms that we're going to discuss today. Those are going to include deserts, deltas, things called levees, ocean basins, beaches, lava flows, and floodplains. I'll go over each one of those as we go through them. But deposition is always going to occur in a certain spot, and that's where energy is at its lowest. So basically, as wind moves quickly, it'll eventually slow down and begin to deposit things. A river, it will move quickly from its headwaters, and then as it flows down onto more flat land, it will begin to slow down, okay? And then it'll become extremely slow as it meets the ocean, so it's going to deposit a lot of sediment there. The same thing is true of glaciers. As they move, they're going to deposit some sediment and they'll leave it behind at the lowest point of energy. So one place where lots of sand can be deposited is obviously in the desert. So you can get anything from larger dunes, like the ones seen in this photo here. So this like kind of larger pile of sand here, or these mini little hills of sand. These are also caused by deposition of one type or another. These little snake lines can be formed either by wind that blows in a continuous direction, or sometimes as they look more over here, it can be from when the rain comes and then we get these little tiny cracks and the water flows through them, and they sort of deepen over time. This is because the soil is not very good at absorbing water. So when the rain falls in the desert, it falls quickly and then it tends to move around in little channels. This is a delta. Sorry, it says desert at the top. It should say delta. It actually shows both. So this is the Nile River Delta. And so you can see the desert kind of around the delta here, but then this really fertile sort of fan shape is where the Nile flows into the ocean here. And so you're seeing this spread out of the Nile River, and then all this really fertile soil is deposited here. And this is a place that's really, really good for growing things. A beach. A beach is a big kind of depositional landform. So things get broken down by the ocean, shells, rocks, those kinds of things. And as the waves flow into the beach, they're going to slow down slightly and they will deposit that sediment on the edge, and which is why we get those nice sandy beaches. If you've ever been to Hawaii, there are certain beaches in Hawaii that actually have black sand, and that's because the primary material that they're made out of is crushed up volcanic rock. And so they actually, beaches don't always have to be the same color. This is going to demonstrate two kinds of landforms. One is the floodplain. So when a river actually overflows its banks, it'll deposit some sediment and kind of wash out that area in a flat thing. The floodplain is a good place where a river can overflow without causing massive damage. So you'll see floodplains are largely flat areas, and then the levees are little bits of sediment that get deposited along the outer edges of these rivers as they're flowing slowly, and they actually will kind of help keep the river in its proper channel. There are multiple types of lava flows. That's what this AA type means. I'm not going to get into, just for the purposes of this lecture, since I've shortened things. Normally we would talk about all the different kinds of lava flows, but basically you should just know this. Lava can be classified on how quickly it flows and how viscous it is. So viscous is kind of a cool word. Things that have a high viscosity are thick. So think molasses, okay? And things that are low viscosity flow very easily. Think water. So lava can have a a change in how viscous it is, so how easily it flows, and then also how much solid material basically it's made out of, what kind of eruption caused it usually, and what kind of rocks were in that eruption, and those sorts of things. And so we have lava flows like this one, which is it's not moving in a very fluid pattern, okay? And then we can have other types of lava flows as well, where the lava moves in a more fluid motion, okay? But just know lava flow is one kind of depositional landform. If you want to see some really cool examples of lava flow, go back and look at the Hawaii, the most recent eruption of the volcano in Hawaii. There's some really, really striking footage of the volcano erupting and sort of the lava spreading out over the land, if you would like to see that. This is one of my favorite landforms. This is called a glacial erratic. We actually have quite a few of these in Colorado, but basically it looks like a big lonely boulder in the middle of nowhere. So this is one that often causes people to ask questions. So you might be hiking and you're going to see this giant boulder and you would say, how on earth did that get there? And what oftentimes is the answer to that, especially if you see sort of smooth, rounded edges, and then oftentimes these cracks in the middle will also be telling. But this is a big boulder or rock that got moved by a glacier. And so as it was moved around by the glacier, it gets these sort of rounded edges. But then the glacier melts eventually and has left behind now this silly looking boulder. And that's what we mean by a glacial erratic. Erratic means it's sort of not predicted, okay? This is another landform caused by a glacier called a came. And a came is basically just a little hill. But let me explain to you why these little hills are kind of cool. So they formed when a glacier began to melt, okay? And so you can see that in this upper picture here. So this glacier would have all at one time would have been like it would have been all the same glacier, okay, the same piece of ice. But as it stagnates, so that means it stops moving and it begins to melt, it's going to get puddles, okay? And what's cool about the puddles is that as water flows down and into these puddles, sediment is deposited. So what this turns into then is as the glacier melts away completely, we get these like little hills of sediment wherever there was a puddle in the glacier above. And so sometimes these can actually be quite large because maybe there was a big crack in the ice, okay? And as water was flowing down here for quite a long time before the glacier melted, we can get a big pile of sediment. So that big pile of sediment will be called a came, which is basically just a hill. And then these little holes that kind of alternate are called kettles. And so sometimes you can get kettles or kettle lakes in regions where you have cames. And that's caused by the melting of a glacier. These are for a landform that's quite common in Colorado. We have lots of moraines, and I know right now you can't go into Rocky Mountain National Park, but sometime over the summer, hopefully you'll be able to go there. That's a beautiful way or place to see moraines. There was a lot of glacier movement in Rocky Mountain National Park, and so I would recommend that you go up there and take a look at some of the moraines. Now there's two types of moraines that I want to discuss here. And all right, so this picture is an excellent, it gives an excellent view of both kinds of moraines. So here I'm just going to notate this as I go. Along the side, sediment will be deposited as it kind of gets away from the side of the glacier. And so these are what we would call the lateral moraines. And then the terminal moraine is this kind of these hills of sediment at the end. So these are deposited at basically the terminus or the end of the glacier. And then the lateral moraines are deposited along the sides or laterally to the glacier, which is where their names come from. Mountains are a landform that can actually be created either by erosion or deposition. So you can either have rock that has been eroded away, creating a mountain, or the depositional form of a mountain is a volcano, okay? Most mountain ranges that we have on Earth are formed from erosion. So for example, the Rocky Mountains that we have in Colorado are eroded remains of sedimentary rocks that actually used to be under the ocean. But if we wanted to look at a different example, so here's our Rocky Mountains. This is actually a picture of the Maroon Bells, which are some of my favorite mountains. I think they're absolutely gorgeous. If you go up into Rocky Mountain National Park, or you can actually also approach them from the Poudre Canyon side, you can see these mountains. These are erosional mountains. We can tell that from a couple of things. One is just sort of if you look at how sharp and pointy these mountains look, and then also we can see that there's all these different features. So if you remember we were talking last time about arêtes and horns and other places where, you know, glaciers can pass through and they cut away at this rock. We can see all of those forms in these mountains. If we compare those to these mountains, so this is a picture from the Andes Mountains. These are volcanic mountains. Okay, so they're going to have sort of this more, and they don't, not all volcanic mountains have the same shape, but they have this sort of even, you can tell that this material has flowed up out of the top of this mountain and then down the sides. So that these are more volcanic depositional mountains, just to give you an idea of how to compare those two. All right, we're going to shift gears here a little bit and talk about plate tectonics. Normally in the middle of this, I would talk about earthquakes and volcanoes, which sort of explains how we get from rocks to and landforms to plate tectonics. But because we don't have all the time in the world this time, I'm going to save those and you'll come back to them in 7th grade. So scientists noticed for many, many years that the continents sort of fit together like puzzle pieces. And if you have a globe or a map in your house, I would encourage you to go look at that really quickly. It's not very hard for you to try to figure out how the continents would fit together as puzzle pieces. But for a long time, this idea was kind of thought to be a silly idea, and there weren't many really solidly scientific observations that supported it. And so we're going to talk about how this became more of a scientifically acceptable idea. And there's a meteorologist who's actually a weather scientist, not what we would consider a geologist, who found evidence that the continents had been joined together by looking at fossils. His name is Alfred Wegener, and he noticed that he could find similar fossils on different continents. And then if you put those continents together, the area where the similar fossils were would be next to each other. And so he called his idea continental drift. And said that the continents moved over time and they moved apart from each other. However, when he first came up with this, people pretty much universally thought he was crazy and said that he, was not correct. It wasn't until the 1960s so that scientists understood how correct he actually was. And his idea basically turned into our modern theory of plate tectonics. And what plate tectonics basically states is that there are different layers of the earth. And so you guys have learned this, you've been learning it since you were very little. There's a core of the earth, then there's a mantle, and then there's the crust. And the crust, basically, we could essentially say floats, although that's not entirely correct, on top of the mantle layer, okay? And because the crust is floating, it can shift and move around, which can cause the motion of the continents that we've seen over time. Let's briefly talk a little bit about the layers, and then we're going to come back to this concept of plate tectonics. So the layers. First, the Earth has a core. It's made up of very heavy metals like iron and nickel. It doesn't play a huge role in plate tectonics, but it is a source of heat for the layers of above, which is going to be important. And then there are two cores. You may know this, the outer core and the inner core. The inner core is solid, nickel and iron, and the outer core is liquid. The cores are really important for actually contributing to the magnetic field of Earth, which is something that we use for all kinds of things, including navigation with compasses and others. And so scientists think that this magnetic field is caused by the rotation of the liquid outer core. So the outer core begins about 2,000 miles below the surface, and it's about 2,200 miles thick. So if you were, I'll show you a picture of that in a minute, which will kind of help you see how big it is to scale. So if you're having trouble picturing that, just hold on a second. The mantle is maybe made up of very hot but not molten rock. So a lot of people tend to say that the mantle is made up of molten or what we would consider maybe like liquid rock. But it's not quite there. So the material in the mantle is really dense, and about 80% of the volume of the earth is made up by the mantle. So if you were to kind of take a slice out of the earth, most of that volume would be made up of the mantle. And the mantle is a solid technically, but it does flow. And so the material in there flows in a very slow convection current. So it's not moving around like a liquid like water would, but it's also not behaving exactly like a solid because it flows. The mantle actually gets hotter as you move toward the core and cooler as you move toward the surface. And so if you remember back to when we were talking about oceans, we talked about convection currents and that warmer things rise and cooler things sink. Well, if we imagine the earth as sort of, here's the core, okay, here's the mantle, and then this is the crust up here, okay. So the core is heating things up and causing that rock that's there to rise. But then when we get to the crust causes it to cool down, and then it begins to sink. So we get this convection current in the mantle that's much like the current that we had in the ocean. Okay, this is called a convection current. Now, this convection current in the earth is moving much, much more slowly than the convection current in the ocean would. Okay, so the mantle, just to give you an idea of how big it is, the mantle begins about 20 miles beneath the surface and is about 1,800 miles thick. If you live all the way north in Fort Collins and you were to drive all the way down to South Loveland, you might be able to go 20 miles, okay? So if you imagine driving that distance sort of straight down into the earth, you would just barely get to the mantle. And it's about 1,800 miles thick, which would be long enough for you to fly pretty much across the United States. The crust is the layer of Earth that's most important for life, obviously, because it's everything we know lives on it, but it's also the thinnest layer of the Earth. So if you were to sort of take a slice of the Earth, it would make up the smallest portion. The crust is made up of solid rock. Obviously, it would be difficult to live on it if it were not solid. And it goes to about 20 miles below the surface at its thickest part, but there are many places where the crust is much thinner. Okay. The crust is divided into these sections called plates. So if you sort of imagine that you baked a cookie, okay? And when the cookie gets out, you sort of take it and you punch it, okay? As you did that, I don't know why you would punch a perfectly nice cookie, but let's say you did. The cookie would break into several chunks, okay? And you could probably piece those chunks back together pretty well. They might not fit exactly, but you would now have a bunch of, different breaks and cracks in your cookie. The crust looks the same way. It's divided into these sections that kind of look broken apart called plates. And the land masses that we call continents, so you guys learned when you were very little about the 7 continents, those are part of one or sometimes multiple plates that are floating above the ocean. Okay, now floating is not at all the correct term. I shouldn't have even used that word because the crust is attached, right? So it's all attached even under the water. So you shouldn't get the idea that the continents are sort of floating in water. That would be wrong. However, the plates themselves are sort of floating on the mantle of the earth. So there are two basic types of crust. I'm not going to get too much into this because we're going through this in a sort of different way than we normally would, but they are categorized on two features, their thickness and their chemical composition. So we have the crust that's under the ocean. The crust that's under the ocean is special because it's the thinnest part of the crust. It's made up of a special rock called basalt, which is a igneous rock. And because this crust is so thin, this is often where we drill for oil and other things. This is also where people thought that maybe we might be able to drill a hole through the crust into the mantle to kind of study it more, but so far any attempt to do that has failed. The other kind of crust is the continental crust. This is what we live on, and as opposed to the oceanic crust, which is composed of basalt, the continental crust is mostly composed of granite or granite-like rocks. And also the continental crust is in general thicker than oceanic crust. However, it varies greatly in thickness from place to place. Imagine places like the Himalayas as being more thick, and then other places as being thinner portions. So all the thickest parts are under are under mountains. The thickest parts of the crust can be about 40 miles thick. That's really far. If you were to drive from Fort Collins to just south of like Longmont, or almost to Denver, you would have driven about 40 miles. The continental crust, because it's made up of granite and not basalt, is actually less dense than the oceanic crust. So if we were to imagine sort of the crusts floating on the mantle, we would have the continental crust floats slightly higher than the oceanic crust. So I'll put an O for oceanic, C for continental. And so this is why the oceanic crust actually sort of sinks down into the mantle, which is why the ocean is there. So it doesn't sink down because the ocean is there, but it sunk down because it was made up of more dense rock and the ocean's collected there. Here's that picture I was talking about just to give you an idea of what the structure of the Earth looks like. So we have our inner core, solid, outer core, which is liquid. That's going to rotate, causes the Earth's magnetic field. Then we have our mantle, which is not quite a liquid, but it does, it's a solid that moves and flows over time. And we get these convection currents in here where things are heated up by the mantle, they rise towards the crust, and then they sink. So the mantle is a moving body, okay? And then on top of that, we have this very, very thin layer called the crust. And that crust is broken up into plates. And because the mantle is moving and sort of has this convection current, those plates are going to shift from time to time. So now we're back here to plate tectonics. So plate tectonics explains what causes earthquakes and volcanoes and other motions that we see in the crustal plates. Earthquakes happen when two plates run into each other for some sort of reason. And there's like a snag or a motion, and there can be different kinds of earthquakes that are caused by different kinds of motions in the crust, but that's usually what's going to generate an earthquake. If you want to go look up a map, I'm not going to take the time to do that in this lecture today, but I would encourage you to look at a map of where all the volcanoes are in relation to the boundaries of the tectonic plates. It's pretty interesting. Almost all of the volcanoes are right along those boundaries to tectonic plates, because that's a good place for the lava to flow from the magma, basically to flow up through the surface of the earth, become lava, and cause a volcanic eruption. So we have two parts of our mantle here, and I want to point out this drawing here. So the top part is the lithosphere, and then this bottom part is the asthenosphere. So both of those are parts of the upper mantle. And so we have rocks in the asthenosphere, which act like they're flowing in that convection current I talked about, and they drag that continental oceanic crust along. So as those plates are dragged and moved along by the mantle, they can't move very far before they bump into another plate. Okay, and if you imagine sort of that you're in a very small bumper car arena and you've filled the place almost full with bumper cars, but there's just enough room for them to kind of move around and turn and all those things. That's what the plates of the earth look like, and they bump into each other quite frequently because of that arrangement. So the line where they meet, we would call a boundary. And when those plates meet or move around each other, there are three basic ways that they can interact. The first is a convergent plate boundary. So if you take your hands, take both of your fists, and sort of make a motion like you're punching them into each other, okay? You're pushing against your two fists against each other. Now, if your fists are pushing exactly equally on each other, then nothing much happens here. Where a convergent plate boundary gets interesting is if the plates are of different densities. So now if you can imagine putting your hands one on top of the other and pushing them together, okay? Your hands begin to, one moves over and one moves under. So now we would call this a subduction zone because one of your hands is going under the other hand. It's being forced down and the other hand is going up and over it. Subduction zones are where we get trenches like the Mariana Trench and also volcanoes. You can see a really good example of convergence if you look along the side of the coast of South America. So we have mountains right there on the continental plate where the crust kind of got pushed up. And then we have a trench on the other side where the other plate was subducted. So if you look here, right, so mountains, the Andes Mountains. And then right along here, if we had a bathymetric map, what we would see is that there's a sizable trench that runs along the coast of South America here. And you get features that look like this, which is Machu Picchu. So now we had oceanic and continental, so they're of different densities, so one goes over and one goes under. If we had two oceanic plates collide, then subduction will still happen. We get deep ocean trenches again formed by those volcanoes, which can create island arcs. So if you remember looking at the Mariana Trench, which is going to be right here, there's a whole arc of islands that comes along these trenches, that comes along kind of in front of this trench. So there's a whole arc of islands here. You can also see right here the Philippine Islands are right here. And then just to the side of them is the Philippine Trench. So these are along plate boundaries. And so we are going to get trenches and then also volcanic islands. Now, if two continental plates collide, the plates will sort of wrinkle up and crack. The Himalayan mountains are the result of, so here's an aerial shot, satellite picture of the Himalayan mountains. But you can kind of see where they got wrinkled up here, which was the result of two convergent plates sort of smashing into each other. So that's going to cover convergent plate boundaries. Now, divergent means to move apart from or to move away from. So if two plate boundaries are moving away from each other, we're going to get different interactions, okay? Most divergent plate boundaries are found under the ocean, and they are found at those mid-ocean ridges that we talked about. And so the longest mountain chain in the world is a mid-oceanic ridge. But sometimes we can get divergent plate boundaries on land. This is just kind of, this is a picture that can help you visualize what that would look like. So you can see this in multiple places. So like if you could see, it's hard for us because we can't see the mid-ocean ridges and the rift valleys. But here you can visualize what that would look like with the two pieces here and then sort of moved apart from each other. This is just a picture that illustrates all three types. We did not talk so much about this transform plate boundary, but that's one where they move, the plates are moving side to side past each other. We did talk about divergent boundaries. So we can have a continental rift zone, which is what I showed you here, or we can have a oceanic, like the Rift Valley here and the mid-ocean ridges. Okay. We can also have convergent boundaries that lead to trenches on one side and mountains on the other. Or we can have convergent plate boundaries of two oceanic plates, which are going to result in a deep ocean trench again and an island arc. The final one that we haven't talked about is when we have two continental plates that are converging, and they would create a big mountain range like the Himalayas. And that is it for geology, which is our last unit for the year. Thanks for sticking with me through all of these online lectures. I hope to see you guys at school next year.